Hi, in this video I am going to go through the OCR A Level chemistry paper. This is paper 2, the 2021 paper, and this is the second half of the paper. I did the first half in an earlier video. Okay. Right, question 19. The question about organic synthesis. This chemical prenal is used in the synthesis of some pharmaceuticals. The systematic name for this, well, we've got an aldehyde group there. There's al, we've got 1, 2, 3, 4. So it's going to be, we've got a methyl group on number 3. So it's going to be 3-methyl but 2-ene al. That's the name. Right, complete the flowchart below for the synthesis of 2 compounds starting from prenal. Okay, right, let's do the left-hand side thing first, all right? So what have we done here? Well, we started off with an aldehyde functional group, and here we've got an ester. So I'm thinking that they must have oxidized the aldehyde group here to a carboxylic acid. So the intermediate is going to be the carboxylic acid. So let's draw that. Okay, and we're going to have 1, 2, 3, 4. Sorry, we're going to have the carboxylic acid group there like that. Okay. Now, how do you do that? Well, it's an oxidation step, isn't it? So you need an oxidizing agent, which would be potassium dichromate. And don't forget, it's got to be an acidic solution, so some sulfuric acid. Okay. Now, the next bit, when they made the ester, well, what ester have they? What alcohol have they stuck on there? Well, they've stuck this alcohol here. We can see that is carbon 1, 2, 3. So it's propan-2-ol, isn't it? With the alcohol with the group on, that was on carbon number 2. So you want propan-2-ol there. And of course, carboxylic acid and an alcohol use an acid catalyst to esterify them. All right, let's go to the right-hand side. Well, NaBH4 is a reducing agent, isn't it? And what will that do? Well, it will reduce aldehydes to primary alcohols. So that we're going to get there, instead of the aldehyde, we're going to get the corresponding alcohol. Okay, so the double bond's still there. And we've got an OH there. Right. Let's see what we're doing with this one then. So we start off with that. By the time we get to the bottom here, well, we've got rid of the double bonds somehow. I mean, that's gone, right? And also they have, like the alcohol, they've actually made an ester. So this is, they put this, that carboxylic acid, 2 carbons long. That will be ethanoic acid, won't it? So that's what they've done there. So the first step is to get rid of that double bond, I think. Okay. So how do you get rid of a double bond? You reduce it, you use hydrogen and the nickel catalyst. So we're going to have no double bond now. Then the next step is esterification. Once again, it's an acid catalyst. And which acid do we need to? What have we done there? We've actually stuck on, as we said before, I think it's 2 carbons long, that carboxylic acid. So the reagent, you can see there. What's that? That's ethanoic acid. To make the ester there. Okay. Is that part complete, I think? 7 marks for all of that. Right. Got more organic synthesis now. Right, let's have a look at this. A student intends to synthesize compound A from chloromethylbenzene. Okay, it's 2-stage synthesis. So we've got to think, what's that intermediate? Well, what's happened here? You've got an extra carbon stuck on the chain there. Now, whenever you do that, they must have gone through a cyanide, mustn't they? Okay, right. Plan a 2-stage synthesis to prepare, and we won't worry about the masses so just yet. We'll just work out the reagents, starting from chloromethyl. But assume, we don't worry about the percentage yield and stuff. Do that later. In your answer, include the mass of it required. We'll do that afterwards. The reagents and equations where appropriate. So we'll do the reagents and equations first of all, then we'll do the percentage yield calculation after that. Okay, so what's this intermediate here? Well, you need to have, it's going to be a cyanide, isn't it? Okay. So you've replaced that chlorine with a CN, nitrile now. Okay. Now what reagents do you need to turn the chloromethylbenzene? Right. You are going to need for that reagent, for that step, you're going to need potassium cyanide in ethanol, dissolved in ethanol. It's quite important, not dissolved in water, but ethanol. Right, so you're going to get the cyanide. Then how do you turn a cyanide group into a carboxylic acid? Well, if you remember, it's basically you are hydrolyzing, you're reacting the cyanide with water. So you actually going to use hydrochloric acid, usually hydrochloric acid, and you boil in a dilute solution of hydrochloric acid, and you'll hydrolyze that. Right, let's do the equations for those two things, and we need to write the equations first. Right, the first thing, you've got the chloromethylbenzene plus KCN is going to form that. The nitrile group, and we're going to get KCl to balance the equation. Now let's do the hydrolysis of the cyanide to form a carboxylic acid. Okay, so got that, and we're going to react that with water, and we're going to get carboxylic acid group. And what's the other thing we get? What happens to the nitrogen in the cyanide? Well, you can probably see that forms ammonia. Okay, but we've got to be a little bit careful there because, right, first of all, we're going to need 2 waters, aren't we? Yeah, because we need 2 oxygens. Well, we've got 2 oxygens, 1 there, 1 there, and we've got 4 H's, 3 there, 1 there. But we're going to be a little bit careful because it's in acid conditions. We're going to end up with NH4 plus, not NH3. So I need to change that. And of course, we're going to need a NH plus on this side to balance the equation. Okay, so that's the other equation there. Now we need to get on to the percentage yield calculation that is asking us. Right, so it tells us that we want to make 5.44 grams of the product. Okay, and it says we can assume we're getting a 25% yield overall, so that's including both steps. Right, so we need to work out the moles of this product, so we need to know its MR. So that is going to be the MR of that. Well, it's going to be 77 for the benzene, C6H5, plus 14 for that, plus 12, plus 16, 16 again, and so that works out to be 136. So we want to make 5.45 grams of it. Let's work out how many moles of that is. Okay, so moles of product A, mass over MR, equal to 5.44 over 136, and that works out to be 0.04 exactly moles. Okay, so we can see here 1 mole of our starting material gives us 1 mole of cyanide, which then gives us 1 mole of the acid. So if there was 100% yield, if there was 100% yield, we would need 0.04 moles of starting material, sorry. But it's only a 25% yield, so it's kind of common sense. You can see that you're going to need ×4 of that, aren't you? So that's going to be equal to we're going to need 1.16 moles of that. Okay, so what is the mass of 0.16 moles of the starting product? So mass is equal to moles times MR. Right, what is the MR of this stuff then, of the starting material? Starting material, to remind you, was right, benzene ring, CH2, and a chlorine. Right, the C6H5, that weighs 77, CH2 is 14, chlorine, of course, is 35.5. So the MR for that, add those up together, what we get 126.5. So let's put those numbers in here. How many moles of it have we got? 0.16, MR 126.5. That gives us a mass of 20.24 grams. That's how much we need to start off with. We need to start off with 20.24 grams of the starting material in order to get the mass of that we require. Right, so that is the end of that question, that part of the question. All right, now we are on to reactions of phenol. Okay, so we've got phenol reacted with NaOH in this first stage. What happens is we remove a proton to form the phenoxide ion there. Okay, then in stage 2, we're going to react that with carbon dioxide, which is not a reaction we're familiar with at all. But you can see it's basically some kind of it's a substitution reaction because we stuck the carbon dioxide, essentially we've stuck it on there now, haven't we? We've swapped it for the hydrogen. It's a substitution reaction. It's probably going to be electrophilic substitution reactions because that's what benzene rings always do. And the last stage, we're just going to protonate it to add some acid to stick an H onto the carboxylic acid group there. Right. Complete the mechanisms for stage 1 and stage 2. Let's do that. So stage 1 is fairly straightforward. Right, that OH minus has got to pull off the hydrogen, hasn't it? So that's going to, that lone pair is going to go onto there, and then the pair of electrons in the bond is going to go onto the oxygen. So we've got, what else we're going to make there? Well, the OH minus has picked up a proton to become water. Okay, so that's now the OH minus is acting as a base there. I think they asked that later on, but it's obviously acting as a base, it's accepting a proton. Now, this is a little bit outside of our comfort zone, really, a little bit, because we haven't come across this reaction. We've got to do the mechanism. Well, let's think. We know that benzene tends to undergo benzene rings and electrophilic substitution reactions. Okay, and so would carbon dioxide be an electrophile? Well, maybe it would, because we'd have a delta positive on the carbon there. Yeah, right. Now, what happens in electrophilic substitution reactions? Well, a pair of electrons jump out of the ring, don't they? The delocalized electrons onto there and form a bond to that. So our intermediate we're going to draw will be like this. And we've got our carbon there. Now, when the carbon can't form 5 bonds, can it? So what's going to happen is one of the pi bonds is probably going to break and go into the oxygen. We're familiar with that happening. Pi bonds breaking and doing that. We've come across that before. So we're going to have that. Now, how about the delocalized electrons? Well, we've partially broken the delocalized electron, haven't we, system? So we're going to draw that incomplete, like that. And important to remember that we've got a positive charge on the benzene ring there. Okay, this is a sort of standard electrophilic substitution. And we usually draw the hydrogen on there to remind us that it's actually there, don't we? And in the final step of the mechanism, what happens is the pair of electrons in that bond, they go back into the delocalized system to reform it, and we've got our final product there. And what will be released? Well, this hydrogen will come off as an H+. So that was a little bit difficult, but it's essentially the same electrophilic substitution reaction that you're kind of familiar with NO2. It's the same mechanism there, really, isn't it? Very, very similar. And you are familiar with that. Okay. Well, okay, what are the roles of the OH minus and CO2 in the mechanism? The OH minus, we said before in step 1, we said, right, it's acting as a base, it's picking up a proton. And the role of the CO2, well, that is an electrophile, isn't it? It accepts a pair of electrons out of the benzene ring. Okay. This is looks a bit tricky at first. 2 molecules of salicylic acid can react together in the presence of an acid catalyst to form compound B. Okay, so an acid catalyst, mind you, that doesn't really help so much because a lot of reactions are catalyzed by acids, aren't they? Okay, but we have got an alcohol and a carboxylic acid on the salicylic acid, so maybe we've got some kind of esterification going on here. It's a possibility. Right, we've got our salicylic acid there, which is C7H6O2. You work out its formula, and we know that that's got to go to form this product, which is C14H8O4. And we know there's 2 of those. Now, if you look there, the carbons are all accounted for, but what we are missing, we are essentially missing, well, we had 12 hydrogens here. Now we've only got 8 on the other side, so we are missing 4 hydrogens, and we've got 4 oxygens here. Sorry, that should be 3. That's wrong there. Got 3 oxygens in salicylic acid. We've got 6 oxygens there, and we've only got 4 there. So we're missing like 2 oxygens and 4 hydrogens. So I think we can probably safely say that that's coming off as H2O, 2 water molecules there, yeah. And we were saying before, the acid catalyst esterification, we're making 2 molecules of H2O. We've got an OH and a carboxylic acid. This is, can you see that this is probably what's going to happen is, what's happening is you get another salicylic acid here, kind of upside down. That's a carboxylic acid group on that one. Okay, and the OH in that one, and that's going to form an ester, and that's going to form an ester. And then that would give us a molecule with 3 rings in it, because it says it's got 3 rings. It's got 2 benzene rings and 1 ring formed by the catalyst. So let's just write the equation to show the structures, showing the structures of the organic compound. So we've got the 2 salicylic acids here. Okay, and how's that going to form? We've got 2 of those. And what's the ester going to look like? Well, we've got 2 ester linkages, isn't it? Okay. We've got that one there. And we've got this one the other way around. There. That is our 3 ring. That's our compound with the 3 rings in it. Okay. right now. A student reacts phenol with nitric and sulfuric acid. Okay, so what's going to happen there? Nitric and sulfuric acid, phenol will react with them. You're going to generate this electrophile, aren't we? Probably, and we're going to nitrate the benzene ring. We're going to get electrophilic substitutions going on. Okay, somewhere on that ring, okay, we're going to stick one or more nitro groups on to that ring. The student purifies the crystals by recrystallization. Describe how you carry out recrystallization. 3 marks is a fairly standard. So what do we do? Recrystallization, you dissolve. It works on the fact that most compounds are much more soluble in hot solvent than in cold solvent. So you dissolve the impure stuff in a minimum volume of hot solvent. So minimum and hot are the 2 key words there. Right, you allow it to cool. As it cools down, solubility decreases and you'll get a supersaturated solution. And so the crystals will come out solution, yeah. Okay, how do you remove the crystals? By vacuum filtration. Once you've got your filtrate, what you do is you wash with a small amount of cold solvent. Okay, wash with cold solvent and you've got your pure crystal. That's the sort of standard question on how to carry out recrystallization. Now, we've got to try, this is the next bit of the question, is we've got to identify what C is, because there's some NMR and stuff. Right, they give us a percentage mass stuff here, and we've got to work out the empirical formula. Okay, so I've done that here to sort of speed things up a bit. Right, so the red line, that's the percentage. So that's how many grams of each one you should have in 100 grams. We want to get a ratio of moles. So how do we turn our masses into moles? And this blue line here, well, we divide by the atomic mass, 12 for carbon, 1, so on. So we've got our ratio of moles there. How do we simplify that? Well, we divide by the smallest number we've got there, which is 1.31. So we do that, we end up with a 2 to 1, the green line, a 2 to 1 to 1 to 2.33 ratio of, okay, so how do we get rid of that a third? Well, we multiply everything by 3. We end up with that ratio there, 6 to 3 to 3 to 7. So that is our empirical formula of our compound. The question tells us that the MR of it is 229, so that does add up to 229. So that all looks good. Okay, now we've got our we have got our formula there. Well, let's have a think what was going on. Okay, put some space here. Where I'm going to do it. Okay, yeah, all right, and it gives us the carbon 13 there. Okay, so I'm just going to draw. All right, we started off with phenol. And what have you got? We've got the empirical formula is C6H. What was it? C6H3 N3 and O7. Now, hopefully we can see what's going on there, right? We have got, well, we started off with a benzene ring and we haven't changed the number of carbons, so there's 6 of them, so that's all good. And we had a phenol there. Let's put that on there. Now we have we know that because we're reacting it with nitric and sulfuric acid, so we're going to nitrate it. We're going to stick NO2 groups on there, and you can see that we've got 3 nitrogens and we've got 6 extra oxygens. 6 that, well, one's in the phenol. We've got 7 altogether. So it's quite clear that we've actually got 3 nitro groups, haven't we, on that we stuck 3 NO2s on to the phenol. Now, this little bit here, it tells about directing. So if you've got an OH group, it says it's 2, 4 directing. So that means when you get substitutions, you tend to stick, it will tend to, so the nitrate will go there, preferably on number 2, or there, which is number 4. And of course, that one there is number 2 as well. So it will go in those positions. Okay, the nitrate, the NO2 will go in those positions. It won't tend to go on 3 and 5. Okay. Also, once it tells you, once you've stuck an NO2 group on there, and we've stuck an NO2 group on that, that's going to go on positions 3 and 5 relative to that too. So it's going to go to that one, sorry, that one again, and that one. So the most likely product we're going to be getting here is 2,4,6 trinitro phenol. I'm pretty certain we're going to get that. We're just going to, let's see if how the carbon 13 data kind of fits in with that. Okay, so I'm just going to make a bit of space here. Right, and we can see carbon 13 data, we've got 4 peaks, so we've got 4 carbon environments, haven't we? So let's just check our 2,4-dinitrophenol. Let's see if we do that. Right, so put our phenol group up there. Nitro there, there, and there. How many peaks, how many carbon environments have we got there? Well, we have got, that one is unique. Okay, those 2 are the same. Those 2 are the same. I'll draw it as an open circle, yeah. And finally, that one is unique. So we have got 4 peaks there. And that's what we've got in the carbon 13. So that seems to be consistent with that. So I would say that is, I'd probably leave that as my answer. Okay. Well, what you could do, just also the chemical shift don't give a great deal of information really here, because it's just, they just all fall in the range of aromatic carbons, don't they? Around 100, between 120, 160. So that doesn't really help us that much. But we have got 4 different peaks, 4 different environments. I just think if we just had a sort of play around and let's put those nitros in somewhere else. Let's say we had them there, and then one on there. Okay. Now that wouldn't give us 4 peaks, would it? Because I think each of those carbons is unique on the benzene ring. That would give you 6 peaks, so it wouldn't be, that couldn't do it. Now let's just play around again, move them a bit more. Let's take those 2 off. Let's put the nitros down here. Right, now that one would give us, right, that carbon's unique. These 2 are the same. These 2 are the same, and that's unique. So that would also give us, actually, it would give us 4 peaks, wouldn't it? But I think the 246, this one, due to the information, the directing effect, the 246 is probably more likely. And I think if you look at the mark scheme, they give you the marks for either of those, but I think 246 seemed to be the kind of logical one to me. Okay, so some more structure determination stuff coming up, I think. Okay, question 21. Right, we've got these isomers with the molecular formula C5H10O. Now we can tell from the ratio of carbon to hydrogens, well, that's CnH2n. That means this molecule must contain a double bond, either a carbonyl or a carbon-carbon double bond. Or if it doesn't contain a bond, it must be, it's cyclic. Okay. Right, let's have a look at E and F. Okay, E and F are, they both give us a reaction with 2,4-DMP. So they both contain carbonyls, don't they? These contain carbonyls. Now they contain a carbonyl. They can be aldehydes or ketones. But let's have a look. There could be aldehydes and ketones, but look, if you react them with dichromate, acidified dichromate, you don't get a color change. It stays orange. So that means that you can't oxidize that carbonyl any further. So it's not an aldehyde. They're both ketones. Okay, they are both ketones. E and F are ketones, and they can't have because of the number. They can't be cyclic. They must be linear because of the number of hydrogens in there. Yeah, they've got 10 hydrogens. Let's look at compound D then. Now it tells us one of them is alicyclic, and it's certainly it's got to be D by elimination, hasn't it? And does this fit in with it? But it does fit in. There's no reaction 2,4-DMP, so that suggests that compound D doesn't contain a carbonyl, right? It can, if you look here, you get a color change when you reflux it with acidified dichromate. That means you can oxidize it. So that means it must be, it's not carbonyl, but it must be an alcohol, and it must be a secondary or a primary alcohol. Right, and we know it's got a ring in it. So let's just try, let's try and work out what D is, because it gives us some carbon-13. We'll come back to E and F in a minute. Let's do what D is. So what do we know about D? We know that it's got a secondary alcohol, it's got a ring in it, and no ketone. Okay, so there's 5 carbons. Let's just say there's a 5-membered ring. And put an OH anywhere, doesn't matter where I put it, is it? Right, pretty certain that that is what D is. Let's just check our data, our carbon-13. Well, will we get 3 peaks? Yeah, that one is unique. These two are the same as each other, and these 2 green ones are the same. So that would give us 3 peaks in the carbon-13, which is what we get. So that's consistent with that. Now these 2 peaks are 24 and 36. If you look down here, they are just like carbons which are not attached to they're not attached to any electronegative elements or benzene rings or double bonds or anything like that. But this one here, 73, that's a little bit on the high side, and that would be consistent with the carbon bonded to an oxygen, which is that one there. Okay, that one's the ppm of 83 of 73. That would fit in. Now, just to show you, well, it is almost certainly that it couldn't be anything with like we could have a ring with 4 in it, an alcohol. It's a secondary alcohol, that's fine, and stick on. We could stick a CH3 there, couldn't we? Incidentally, we couldn't stick a CH3 there because it would make it a tertiary alcohol then, wouldn't it? And it's going to be, no, it's not tertiary because it does react with dichromate. But if you put your CH3 there, I think you'll see that you have got how many environments, carbon environments we've got. They're all different, those carbons. That would give you 5 peaks, and you don't have 5 peaks. Or let's say if we put the methyl there, how many peaks would that give us? Well, that will give us 3 peaks. So that oh no, would it give us 3? Let's see, how many would that give us? You get 1 there. These 2 are the same. Sorry, that would also give us 4 peaks. So that will give us 1. So that is, it conceivably could be that as well. D could be, the 5-member ring or the 4-membered ring. And I think it could even be one with 3. It's possible that it could be. Let's have a ring with 3 in it. We're going to have to stick 2 carbons on there, 1 there, 1 there. That will also give you, I think that will give you 4 peaks in the spectrum, won't it? Oh no, that's not got enough. That hasn't got enough carbons in that one, has it? What I'm talking about. Sorry. Wrong, beg your pardon. How many peaks would that give us in a carbon-13 spectrum? That one's unique. These 2 are the same, and these 2 are the same. So that would only give us 3 peaks, so it can't be that. But it could conceivably be that as well as that. I think you put either one down, you get all the marks. Right, now let's look at the 1H NMR spectra of E and F, and they've left the integration data out to make it a bit harder. Okay, so let's have a look at them. Right, let's look at compound E first of all. Now, It is C5H10O, and it's got a carbonyl in it, isn't it? And it's in a straight line, right? So we've only got 2 environments. So that suggests that we've got quite a bit of symmetry. We've only got 2 hydrogen environments. That suggests we've got to have quite a bit of symmetry there. Because if I put, well, let's say if I put the, there, I'm going to have hydrogens here, hydrogens here, hydrogens here, hydrogens there. 1, 2, 3, 4. That's going to give us 4 environments. We've only got 2. So I think it should be fairly obvious. How do we make that symmetrical? Let's put the carbonyl into the middle of the 5 in a chain. Let's do that. I'll draw out the CH's. So we have CH3, CH2. Let's put our carbonyl as a middle carbon. CH2, CH2. Now that would give us just 2 environments, wouldn't it? Because those hydrogens are exactly the same as those, and those ones are the same. Sorry, those ones are the same as those ones. Yeah. Right. Let's look at the red hydrogens. What would they give us? Well, what would be the splitting of that? We'll look at the carbon next door. You have got 2 on there, so that would be a triplet. So that would be the red. That would be the red hydrogens. Okay, that's them. Would that have a ppm of about 1? Yes, it would, because it's not near any electronegative atoms. So it's going to be down, in that part. There's the ppm scale there. And let's just check the green ones. Well, the green ones, what's going to be the splitting of those? Look at the carbon next door. You've got 3 hydrogens there. So 3 plus 1, 4. It's going to be a quartet. Yeah. ppm should be about 2 and a bit, a little bit more than 2, because look here, when you have a carbon, when you have hydrogens next to a carbonyl carbon, it's usually about 2 ppm. So that is compound E. Right, let's have a look at compound F. Right, it's a bit more difficult there. So they've got a multiplet there, that's split into 7, okay? So that means you've got 6 hydrogens next door. So that suggests we have got a hydrogen like that. Now, how can there be 6 hydrogens on the carbons next door? There must be 2 methyls there, mustn't there? That's kind of fairly obvious. Okay, we've got 2 methyls there. Now, those 2 methyls would be then probably this peak here, yeah, low ppm, because it's not near carbonyl, whatever. And the carbon next door to for those hydrogens, well, there's 1 there, isn't it? So it'd be a doublet, and that's what we're getting. We're getting a doublet. This hydrogen would split those signals into a doublet. Now we've got 3 carbons. We've got a carbonyl to think about, and we have got another. So let's see what we could have. We could have a carbonyl there, couldn't we? And a CH3 there. And I think it's got to be that way around, because we know you can't be an aldehyde. It's got to go in the middle somewhere there, hasn't it? And let's just see what would be the splitting of these hydrogens. Well, the carbon next door is a carbonyl. There's no hydrogens on it, so it would be a singlet, and we do get a singlet there. So that is pretty sure that that is what compound F is. It is butane 3-methyl butane 2-one. Okay, and I think that is the last question on the paper. So that's it. Thank you.